But we're excited to be here representing Northrop Grumman. So Northrop Grumman is a huge defense contractor. They do lots of different things, lots of aerospace systems. We originate from the space sector, and even within that sector, there are many, many interesting programs that we work on. So I guess I should introduce ourselves before we go on too far. I'm Brandon Campbell.
Oh, hold on.
Oh, am I off the camera? All right. Where's the box on this?
It's right on the podium.
Okay. So if I'm not like right behind the podium, I'm like cropping my face.
You've got about 2 feet on each side.
Okay. Great. I'm probably gonna, it's just an inevitable, it's a foregone conclusion that I'm gonna spend this whole talk like cut in half. But I'm Brandon Campbell. I am a software engineer and software manager for a team of digital innovators. And this is my colleague, Josh DiGiorgio. He's a systems engineer, and he insisted that I not elaborate any further than that. So I did also want to credit Spencer Shiotani, who is a software engineer, a cognitive software engineer on my team. He helped us put this material together. But he wasn't able to be present today. We still wanted to drop him a line. So today we're going to talk about how at Northrop Grumman we define a digital twin, how we build a digital twin. The content is going to be part philosophy and then part applied. And I insist on the philosophical component because it's really necessary to understand why we built things the way we did. And because we work for a defense contractor, there are a lot of details we can't and won't disclose, but the philosophy that we used to build our digital twin is something that we can share and that I think is valuable to the industry as a whole. So we'll talk about what a digital twin is, because I think that in and of itself is a loaded question, and we all probably have a slightly different idea in the audience. And then we'll show you how we build it. So with that, I'm going to hand it off to Josh.
Yep, sure thing. You want to drive this?
Oh, yeah, I'll drive.
All right. So the type of twin we'll be talking about today is a facilities digital twin. And the big idea is this: buildings with people working inside them are very complex systems. As the size of the building increases and the amount of people working in the building increases, the problem starts to get very, very difficult to manage. We have that problem in Northrop Grumman. I'm sure a lot of your companies have that problem. And so what we did was we built a digital twin, or at least a prototype of one, to help us manage that complexity. So when you think of a digital twin, maybe the first thing that comes to mind is a 3D model. But the reality is digital twins are a little bit more complicated than that. Your 3D model might be a component of your digital twin, but it is not the entirety of the digital twin. As our talk continues, we'll show you how we battle that complexity with graphs and Neo4j.
I was expecting that to drop a little bit harder.
Yeah. So one of the reasons that I like the original Jurassic Park movie is because it touches on the pitfalls of a complex and misunderstood system. In the movie, one character is a single point failure, human in the loop. The character makes a decision to sabotage the system, which eventually results in the demise of the entire park. What we sought to do when we were building our digital twin was to not eliminate the human from the system, but to try to reduce the influence of the human in the loop. Now we're going to cover a few reasons why facilities are a little bit complicated. Workstations, for example. Our definition of a workstation is a location in the building where the employee performs a work activity. But it gets a little bit more complicated than that. if a workstation, if a workplace is a hybrid remote slash in-person model, then you may be asking the question, how can we divide these different workstations between multiple, how can we divide one workstation between multiple people at different times of the day? And when you start asking those questions about your facilities, you're getting into a new a layer of complexity. Another question we asked is, what is the optimal seating arrangement on a given floor for any team? Again, that's not a totally an entirely easy question to answer when you have multiple teams, limited seats, and it turns out that you probably have too many people given how many seats you have available. Another example is, how do we know that the configuration of a floor plan how do we know that the configuration of a floor actually matches this floor plan? And the short answer is, in the beginning, it might. As soon as you get construction people in there, it starts not to match the configuration of the actual design draft. And then as soon as people start working in there, things start changing. I think we're good for the next slide. Whoops.
You got that? Revisit that jump scare there. Okay.
So hopefully you'll forgive us a little bit for our light trash talking of relational database. But our myth is that spreadsheets and relational database are enough to take on this problem. And the reality of that is that we believe that reality does not conform to the constraints of that data structure adequately to take on the problem. Spreadsheet's a narrow view of reality, and if you've ever worked with them, good luck keeping them updated and authoritative. Spreadsheets rely pretty heavily, in some use cases, on humans in the loop, which is something we're trying to reduce in our solution. Now I'm going to hand it back to Brandon. He's going to go a little bit further into how we integrate Neo4j.
So, I mean, this is a Neo4j conference. Obviously, we're going to take a little bit of time to explain why this is a good fit for us. We had a discussion earlier before the talk began about how Neo4j allows us to capture emergence, and because the facilities that we're trying to create digital twins of are so complicated and so dynamic, it's really difficult to anticipate everything that we're going to need to model and everything that we're going to want to need to model in the future. And so the Neo4j is a really great fit for us. There is a little bit more detail as to why Neo4j is a good fit for Northrop Grumman. We use it to manage our digital threads. We'll talk about that in a talk that we're doing tomorrow called Fighting a Multi-Armed Monster. So we'll talk about how Neo4j is involved in a digital thread that we use to hydrate our digital twins. So tune into that if you want to hear more. Today's subject matter is mostly going to cover, here, I want to go touch the screen, but I'll stay over here. This architecture, which we are using for a facility digital twin, but also which we believe can scale to other types of digital twins, and in general is a horizontally scalable digital twinning architecture. So on the right side of, well, yeah, the right side, you're right. We've got the design digital twin, and then on the left we have the reality digital twin. We'll talk more about what those mean, but I want you to keep this architecture in mind as we go throughout the rest of the slides, that we've got these two different types of digital twin that we're reconciling at the top, and then we build our presentation layer on top of that. So now for the philosophical discussion about what is a digital twin. I feel like this is a necessary inclusion in any talk about a digital twin, because in my experience at Northrop Grumman and working with our customers, there is no consensus on what this word means. And as an ontologist, I really struggle to talk about anything without first establishing common ground. So we're all talking about the same thing, and we all understand what this is. So at its core, a digital twin is really nothing more than a digital representation of something. However, the term has definitely gained a bunch of ancillary meaning, as industry has picked it up and turned it into a buzzword. At Northrop Grumman, we've determined that it is necessary and useful to differentiate between types of digital twins. So this is a simple view, top-level view of our digital twin taxonomy. how we break them apart, how we talk about them, because when we're talking with our customers and talking with each other, these terms help us to determine who's talking about what, who wants what, and what you need to have a digital twin. So we differentiate between a design-driven digital twin, a reality-driven digital twin, and a prognostic digital twin. Now this might seem obvious up front, but I tell you it is not. If you don't differentiate between these things, the lines between them blur together, and then it becomes really difficult to solve specific problems or to have a flexible architecture that can adapt to emergent use cases. And we're going to talk more about what differentiates these things, but an easy way up front to kind of keep track of what we mean is that the design digital twin is to capture ideal state of a system. The reality-driven digital twin is to capture actual state of the system, and a prognostic digital twin is to capture the potential state. All of these revolve around the issue of state management, but they are different things. So Josh is going to get into it a little bit more, but the ideal state is going to be anything you planned, anything somebody engineered or thought of or wanted to happen. You know, you can want it all day, that doesn't mean it's real, but it also doesn't mean that you don't need to keep track of what you wanted. So we believe that you need a digital twin to capture that ideal state. The actual state is going to be driven by sensors and observation. It's to represent what actually is. Now you can want something all day, but at the end of the day, what matters is what's actually there. So you need to know that as well. And then the potential state is where we get into trying to get ahead of the game and figure out what will be, you know, and that's where our AI ML analysis comes into the picture. So another important differentiation that we like to draw is the layer of a logical digital twin and a presentation twin. This one is very commonly conflated by our customers. When they ask us for a digital twin, they're thinking about the presentation layer. So it might be some sort of UI, some 3D model, or some AR or VR experience that they want to have. But in order to provide them those experiences, we have to have a logical digital twin. So, and the logical digital twin does not care about presentation, right? And the other point I want to make here is that it's an a la carte kind of system. You don't need to have a design, a reality, and a prognostic twin for every use case. You can have one or two or some combination of them, but any one of them can be mapped onto a presentation twin. So you might use the same presentation layer to show your reality and your prognostic twins, but it is still useful on the logical side of things to differentiate between them so that you can slot them in and out. And then the last element that I'll talk about a little bit is the importance of the digital thread. So the digital thread is also a buzzword that is also overloaded and maybe misunderstood, or we aren't always on common ground when we talk about this. So when I say that this is how Northrop talks about the digital thread, understand that what I mean is this is how our organization within Northrop talks about it, not necessarily the whole company. But the digital thread, in our estimation, is the umbilical cord that connects the digital twin to an influx of data. And it's really important, because you can have a digital twin that's just a snapshot in time, but what people are usually talking about, what they're really getting at, is they want something that can show what's going on dynamically. They want to be able to see the input as it changes. So in order to do that, you need a strategy in place to manage your digital thread, which is just how do you get the data from where it is into your twin, and how do you keep it all straight? And what we'll show you in the second half of the presentation revolves around the way that we groom our digital thread to keep it all nice and tidy when we're generating our reality twin and our design twin, so that we can reconcile them. So a digital twin that does not differentiate between intended, actual, and future state runs the risk of misrepresentation. And if you're going to have a digital twin, then above all else, you want to accurately represent the thing you're twinning. If it isn't accurate, it's not a useful digital twin. So we don't want to send our customers out to make business decisions against a digital twin that doesn't accurately reflect what's going on. So that's why this distinction between state management is so important to us.
I'm gonna have you continue for a little bit. You can keep going with the slides.
Not sure.
But, sorry. Oh, it's my turn?
Yeah.
All right. You want to drive?
Yeah.
Yeah, as Brandon touched on earlier, our design-driven digital twins are going to be in the same category as our ideal state twins. These are ideas of what we want our digital twins to be, not necessarily what they'll end up being. That includes our requirements documentation, our building floor plans, and these are really the precursors to what reality ends up dictating that they become, if that makes sense. Next slide. Just touch a little bit on what's going on here. Part of our requirements engineering actually occurred in a graph. I sat down, as some of you may have, in Confluence trying to write out a single statement or a few statements that describes what our twin is going to look like, our initial requirements. But it turns out that things get so complicated that natural language sentences don't really adequately capture the way we need to describe how the system should ideally be. So we tried it in a graph, and the pink nodes you're looking at are data actors, things we're interested in. The yellow nodes are metadata properties that we believed that these data actors in our system would have. Now, as the system changes, this changes too. So I work hand in hand with our developers. I'm also the product owner for the digital twin we're building. And as they tell me that reality changes, I go back and update the what I call the requirements ontology or the requirements knowledge graph. Some examples of reality-driven digital twins are sensors and human observation. So you may have a temperature sensor in a building, and this is telling you what the reality is in that room. Your design-driven digital twin will tell you what it should be. Your IoT sensor is going to tell you what it actually is. Human observation can also be a reality-driven digital twin. We try not to rely too heavily on this, but if, for example, if a sink is overrunning and you don't have any sort of sensors to check your water flow, your best IoT sensor is actually going to be a person in the bathroom saying, hey, the sink's overflowing. So we're trying to incorporate that as well. Here we have a LiDAR scan with a side and top-down view of a building. And you can actually see how well the details of the building that LiDAR captures. I don't know how visible that is to people in the back, but there is actually a basketball court right, there. You can see that there's 3 levels of the building. There's a basement, and one of the reasons that we like LiDAR is because it's pretty cheap, and it's not a huge effort on part of the human operating the LiDAR machine, and it captures a fantastic level of detail. This is actually a LiDAR scan that we took of one of the relatives' houses of one of the people we work with. And you can see the kind of detail that just a handheld LiDAR scanner gave us.
It's worth noting while we're on here that if you looked at the architectural floor plan for this building, it might look really similar, right? But it isn't going to be exactly the same because the way the building was realized is never exactly the same as the way the building was designed. So the reason LiDAR is so good is that we can reverse engineer floor plans that are not idealized, they are representative of what's actually going on. In Northrop Grumman, that matters because our buildings are not static. The way that they are built and the way that they are used is very dynamic. So they're taking walls down, they're moving things around, they're repurposing things all the time. So when we started our digital twinning journey and we hadn't differentiated between these ideal and actual states, we were building our digital twin on top of a floor plan that was an architectural diagram. And it was immediately apparent that that was going to be inadequate in the long run because reality and the architectural diagram never match up.
As soon as you get people in there, your configuration of your floor is going to start changing. We found it's true in every single floor that we've tried to capture in a digital twin.
Also, the LiDAR is really horizontally scalable. We needed something that could capture actual state in a facility anywhere without installing expensive equipment that could be performed at a regular cadence and could be predictable. And LiDAR answers the mail for that. We can take it to any facility. There are a lot of options for LiDAR, but the ones that we have chosen for this program are handheld. So we just send someone in and walk the facility. We want to keep humans out of the loop, but having a human walk around and scan the facility is an acceptable level in our estimation of human in the loop, because the human isn't actually engineering anything. They're just capturing the sensor information.
The person walking around isn't like drawing a floor plan out. It's
Right.
the LiDAR that's collecting the data.
It also keeps, there may be an argument that you can put a workflow in place to take your BIM model or whatever you might have and update it so that it reflects the current state of the facility. But we submit that anytime you have to have a person come and represent or reverberate what the actual state is, you're introducing tremendous lag and risk, that it's not going to be accurate. Where LiDAR is going to give you something that's quick to get and very accurate, and you can do it over time. So we're going to walk through a little bit now the process that we actually use to curate our digital twin and combine all of the data. So to do that, we use a product called the Vorpal Blade, which we developed for the purpose. So it's an Northrop Grumman product that is built on the concept of ontology-driven data integration. We're also doing a talk about that tomorrow. It's accelerating ML ops with ontology-driven design. So I'm very passionate about the topic. We won't get too much into the relationship between the ontology and the integration in this talk, but I did want to call out that it's involved. It's part of how we manicure our digital thread. So what you're looking at here is a recording of the Vorpal Blade. It is the domain ontology that we use to create the facility digital twin. If you remember back to one of my earlier slides, the structure of this domain ontology mirrors the structure of that diagram that we showed, where you've got your reality leg and your planned leg that are treated separately and then reconciled before we present it to our end users. So in this diagram, we'll dig into each of these domains a little bit further because there's more granularity inside them. So we'll start with the planned sources on the left. So all of our digital twins are ingesting data from different places, right? The digital twin, in a lot of ways, is nothing more than the aggregation and combination of a bunch of data we were already tracking. So in an organization like ours, you might be interested in data sources like this, Active Directory if you're a Windows shop, Archibus for floor plans, Workday is an HR data resource, and something like ServiceNow to manage IT and tickets. These are all ideal data sources, and it can be difficult to differentiate what goes in the plan twin, what goes in the reality twin. The reason we put these things in the plan twin is because they are all about what should be going on, who should be present, what should the floor plan look like, what should people be doing, and what things should be assigned to them. But ultimately, these aren't things that we can observe with sensors. They're assignments, essentially, that management makes and divvies out, and so it needs to be handled separately. The next layer up, so we're still on that plan leg, we have the actual plan twin. So the plan twin is the connected version of all of those disparate sources. So we've taken Workday and ServiceNow and Archibus, and we have mapped them onto this ontology where everything is related. So again, this is a logical model, right? It's not presentation. So we don't intend to show our customer what you're looking at right here, but it is important that we keep all of these things straight so that when we get questions, we can answer them. So you've got a person that could be at a requisition or an actual person, so they might not actually be an employee for the company yet. They might just be a vacancy that we need to fill, but we still have to keep track of them in much the same way. Or it could be an actual record of somebody who works for the company. That person could be a proprietor. That means they might own something, in this case, some kind of device. That could be like a phone or a computer. But interesting thing there is that rooms can also own things, so they're also proprietors, so that's a useful differentiation for us to make. And then you can see off to the right, we've got rooms that are in areas, that are on floors, in buildings, in a campus. So we're mapping all of the plan data onto this. So this is where your floor plans are coming through. This is where all of the employee records are coming through. But ultimately, none of this is real. It's all ideal. So we'll jump over to the reality twin. Some of the data sources you might use on a reality twin could include, obviously we like LiDAR. It could be Google Earth if you wanted a large-scale map or topological view. It could be GPS data. We put a RUCO there. That's really a placeholder for any kind of 3D positioning of some semantic label in 3 space. So if we want to know where things are that relate to our plans, we need a way to basically stamp them so that when we scan them, we know where they are. So we use a RUCO as an example of how we might do that. IT metadata could be, you have to be careful when you're teasing it apart because some of it is planning, right? Like they might keep track of the assignments of who has what equipment, but what we're really referring to here would be something like port activity. What are people doing with their computers, and you know, what is observably true about what they're performing. We like it because we don't have to censor a bunch of equipment, which would be expensive and difficult to scale horizontally, but they're already keeping track of all this IT data, so we can keep track of who's doing what, where, and use that as a source of information for how the space is actually being utilized. And then IoT sensors, my question for you on this would be, how big is your budget? Because the bigger your budget, the more you can do with IoT sensors. So the sky's truly the limit. You can do things like temperature and humidity and occupancy and a ton of other things that I'm not even going to have thought of. So any sensor that is observing actual state could be an input into your actual or reality digital twin. So the reality digital twin here that we're showing you is much simpler than it might be for some other use case. So it's kind of been reduced down to just the bare minimum. But we've got a semantic target that would be your Aruco targets that are associated with 3D points in space that are tied into your point clouds from the LiDAR scans. And then we've got actual floors on actual buildings. These nodes in this graph represent that we know these things exist because we have a sensor reading of them, not because they should be there. So we now have 2 separate records of the floor, the building, the campus, because we're trying to keep track of the fact that they should be there and the fact that they are, in fact, really there. So even though this looks redundant, it is actually semantically distinct. They mean different things. They're just related to the same root. And so that brings us to our reconciled digital twin. At the topmost level, this is where we take the plans and the observations and say, okay, what do we want to present to the world? You know, because the reality is that what our use cases are rarely categorized in such a way that we can neatly say, oh, this is a reality twin problem, or this is a planned twin problem. Most of the time it's some unique blending of the two. And that's why we have this layer on top of it, which is, we just call it the reconciled layer because you can't really say that it's real. It's just whatever we determined was useful from the data that we have. We put it together into some big picture and then present it. So this piece of our ontology is actually facing customers, right? So, I mean, when I say customers, I mean internally to the company, right? Users, employees. They can access this data and see what's going on in the facilities. So again, you've got the same structure: floor, building, campus, location. Location's actually a new one on this layer. But the point is that all of these things have been evaluated independently for a delta between what was built and what was intended. Now, how you do a delta between as built and as planned is going to vary wildly depending on what piece of information you're reconciling, right? So this is not showing you how to do an as-built versus as-planned analysis. What we're showing you is a pattern that we put in place to make sure that everything in our digital twin, end to end, has a spot in our architecture where we can do that comparison. So you still have to solve the engineering problem of how. How do you take a LiDAR scan and reconcile it with a floor plan, right? And we're working on that. That in and of itself is an interesting and complex problem that involves computer vision and algorithms that are outside the scope of our talk today. But the point that I wanted to show is that they're all in there. So I need to pause this video. It's going to run right past me. Ultimately, that's kind of an awkward place to pause it, but what you're seeing on this screen is the actual pipeline that we run to ingest data from all of the different places and combine it together to create all of those layers of the digital twin. So I'm actually going to let it run. We'll see where it lands, but it's color coordinated to match. So the green is the planned twin, the yellow is the reality twin, and the white is the reconciled twin. And when you zoom out, you can see that there's a pattern where we build the plan and the reality first, and then we reconcile them. We're running the pipe right now, and it's actually going and finding the data and defining it. This is really what Vorpal does. I call it a semantic bagging and tagging exercise. So it's just going out and saying, oh, you need this thing. I have all this data. This is where this thing comes from. And it does it one at a time. It never defines anything more than once. And then when you put all of that together, you have a digital twin of the integration process, where you can see what the cause and effect is between pieces of the integration. If you change something upstream, you know exactly what's impacted downstream. And if there's emergence in your requirements, or you need to add something to your digital twin, either the plan or the reality, the impact on your integration, your digital thread, is deterministic. So, and we'll talk more about that in the odd design pattern talk tomorrow. So the important part here is that this is the part of the pipeline that's actually responsible for generating the digital twin. And the output here is a Neo4j knowledge graph, where we have the logical model for instances of all of the things in our ontology. So by using this structure, we're taking data from our plan and our reality. We are combining it together and reconciling it so that we can build a UI on top of it and present it to our users.
So for a little bit on our current implementation, next slide. Our proof of concept was a top-down view of the floor plan, of a floor plan in any given building in any campus that we're covering that's in the scope of our system. We found that people really liked this type of interface, and people who originally did most of their facilities plannings in spreadsheets abandoned the spreadsheet solution for the app that we developed internally for the company. And so quite a few people's jobs now actually revolve 50, 60% around using this one app that we developed. So some of the capabilities are we can track seating assignments, we can propose new ones, we can communicate about big moves going on, display locations of seats, display conference room locations. And one of the most important ones is if you're looking for someone in the building, you can input their name into our query and actually find out where they are in the building. So before that, surprisingly, it was actually very difficult to find people in these big buildings.
That's where they're assigned, right? We're not Big Brother here. We don't have like
Right,
individuals tracking where they are. And I think there's some ethical implications there.
Yeah, we haven't gotten to the point where we're going to slap a QR code on their back, and
But we could.
But so right now we're in the process of revamping. We've got our prototype and our proof of concept out there, and now we're building it a little bit more of an organized way. And so we've got a lot of stakeholders in the company on board and excited for this, and we may have something more to present next year on it.
Yeah, it's an architecture that we believe we can roll out to a lot more parts of the company than just our organization. And the reason we can do that is because this architecture keeps everything in its lane, and we have visibility in how to put it all together. Do you guys have any questions for us?